like little clippy things. Clip them right here. You know, on
Yeah. So far it's working.
So let's take a look at this first one. So you have, it looks like you have two intermediates. You've got Cl, which is not the normal state Cl would be in, right? And you have this thing, which shows up here and disappears over here. So you have two reactive intermediates that can't be in the rate law, okay? So what is our rate law? Rate equals what? K times ClCO times Cl2, right? Because it's whatever you get for the slow step. That's your rate law, okay? But that is not a valid rate law because it has an intermediate in it. The ClCO can't be in the rate law because it's not a reactant that you or product that you actually see or have at the end. Okay? So we have to figure out how to get rid of this. This is what we have to figure out how to get rid of. Okay? Do you see a way to get rid of that? Do we have ClCO anywhere else? It's up here, right?
Yeah.
Okay. So remember that when you got the double-headed arrow, the rate forward and the rate back are equal to one another. So that means that K times Cl times CO is equal to K times ClCO. Obviously there's different Ks. I'll do. It doesn't really matter much because we're going to get rid of all those subscripts eventually and just call it K. So it doesn't really matter. Okay. So now I can substitute in, right? Right? Where I realize this K is actually this K plus this K divided by that K, but whatever, they're all Ks. So we'll just kind of ignore them. Okay, is that a valid rate law?
No.
No, because it's got Cl in it. Well, crap. Okay, so now we got to substitute to get rid of the Cl. Can we do that?
So the top one.
That top one there. So we know that, what's this? We'll call this K1 and K minus 1, I guess. So K1 times Cl2 is equal to K minus 1 times Cl squared. You guys see that? How you get that? Why is it squared?
It's got a 2 coefficient.
Because there's a 2 right there, yeah. That's mean squared, okay? Oh, but hold it. I only need Cl, I don't need Cl squared. So, square root both sides. So Cl is equal to right? Oh, hold it. But I've got, I can combine some terms, right?
Add them together.
Yeah.
Yeah.
Do you see how it's all just substitutions? It's all just simple algebraic substitutions. That's all we're doing. And don't get all worried about all the K's, okay? You got a million different K's up there, but it's like whatever. They're all gonna go away and turn into a new K. So, unless you actually have numbers for K, we don't care. It's not gonna matter. Okay, but notice something that happens here. You notice how you can get exponents that are not integers, right? So, all right. Okay, I walked you through this one, you do this one. There's a really, really good chance that you're gonna see one of these on the test. Okay, so what's my rate law? What's the rate law straight off the off the equation here?
BR H2.
Br times H2.
Yeah.
Right? Okay, but we can't have Br because Br doesn't occur as Br, it occurs as diatomic, right? So you can't have Br in there. So we gotta get rid of this. So let's see, where we got Br? We have BR several places, but this one's probably the one we want to use. So let's see, what do we know? We know that K times BR squared, BR2 is equal to K times BR squared. So BR is equal to K times BR2 1/2.
Yeah.
So it's equal to K times BR2, that's the 1/2, times H2. BR2 sound like something you could actually have? H2, something you could have? Yes?
What's the goal of doing, like, what are you supposed to end up with every time? What are you supposed to limit it to or change it to? So you know-
The goal is that the rate law has to be things that are reactants or products. It can't be something that just is, we just hypothesize in the middle that this is what happens. It's got to be something that you can hold in your hand or in a bottle and say, yeah, I got a bottle of bromine. Yeah, I got a tank of hydrogen. That totally works. But I don't have a tank of singlet bromine. I don't know what you'd even call that. Bromine that's not diatomic. I don't know what you call that. BR. Now, to make life a little easier, if I gave you this on a test, I would probably give you the master reaction, the one that here's the reaction. So it'd be pretty obvious if you don't see it in the base equation, then it's an intermediate, right? Okay, so that's elementary steps. You can break any reaction down to elementary steps, okay? Sometimes you have to invoke intermediates, things that you can't actually measure usually. And whether or not it's right or not. So somebody may propose this mechanism right here. They say, well, that's the mechanism, but they're actually doing it backwards. They did this first. They found out, they used the method of initial rates to find out what X and Y were. And then they say, okay, how can we explain that in terms of elementary steps, and went to find it that way? And so sometimes it's, depending on the quality of the graduate student, sometimes those are right, sometimes they're completely bogus, but whatever. But they have to match up with the experimental data. All right. So this is we're doing kind of a catch-all day to kind of practice a little bit on kinetics before we go on to the next thing. Okay, so here we go. I-131 has a T1/2 equal to 13.1 days. Okay? How long for you got some iodine 131? Does anybody know what you use iodine 131 for? It's actually fairly famous. You actually use that for thyroid cancer. If you have thyroid cancer, you give somebody some iodine.
Yeah, that makes sense.
Iodine accumulates in the thyroid, and so you can get it if you give somebody thyroid iodine 131. It'll go straight to the thyroid and kill the thyroid. Radiation therapy. So really effective tool for thyroid care. Okay, so how long is it going to be before you only have 5% of your iodine 131 left? So remember, you got three equations for first order reactions. You've got just the rate law, rate equals Ka, which it's just like that. And then we've got the integrated rate law, and we've got the half-life equation. So I have half-life, so that sounds like the one to do first. So natural log of 2 is equal to KT 1/2. I know what T 1/2 is. So natural log of 2 divided by 13.1 days is equal to K. Yeah, I don't know, it's a number. What?
0.053.
0.005.
I just have 1 0.
I have 1 0.
0.053?
Yeah.
Okay. Units?
Per day.
Per day, right? It's always reciprocal time. Okay? So now we can pull in the integrated rate law. I know what K is now. How much did I start with?
100.
I start with 100%, right? Sure.
100.
So I start with 100%. And now I have 5%. Solve for T. So 60 days, something like that?
57.
57 days? And you can kind of check your work, like I just did, because I don't know how to do logs in my head. So I go, hey, after one half-life, after 13 days, what percentage do I have left? 50%. Okay, another half-life, another 13 days, how much I got left? 25. After another 13 days, how much I got left? 12 and a half. After another 13 days, what have I got?
6.25.
6.25. So, and then it would be 3. So I'm somewhere between 4, which would be 52 days, and 5, which is 65. So my answer better be between 52 and 65.
Yeah.
And it is, 57. So awesome. But there's kind of a non-mathematical, well, I guess it's kind of mathematical because you got to be able to divide by 2. But you know, a essentially non-mathematical way of checking yourself, right? Because you'll notice if you screwed up and did like 5 over 100, you know, you're going to say like, well, in 0.2 days, it's totally all going to be gone.
It would just be negative days.
Would it be negative days?
Yeah.
Oh, even worse. Okay. You've already missed the boat. It was 5% a couple of days ago. So, all right. Which makes no sense, by the way, but whatever. Okay, well, let's try one more.
No.
So I got some iodine 131, and I want to know what's the rate right now. What's the rate of decay right now? already found?
Yeah. Maybe. Wait. Yeah.
Kinda. It's in the wrong units, right?
Yeah.
But I mean, you can use it, you just gotta convert it to the right unit. What kind of units do I need K to be in?
Per second.
Per second. Yeah,
Wouldn't we need the molar mass of 131 iodine?
yes.
The
Who's buried in Grant's tomb?
Grant.
Grant. What's the mass of iodine 131?
131.
Oh, there you go, yeah.
Yes. Yeah.
Oh, is that micrograms?
Yeah.
Well, let's see, we can do this one pretty easily. So K is equal to 0.053 per day. And in one day, we've got 24 hours. And in 1 hour, we've got 3,600 seconds. So, I don't know. So what's K?
Real small.
It's gonna be real small, yes.
1, 3.
6.12 times 10 to the minus 7 per second. Okay, so now I've got it in per second.
3,600 grams of the. Wait.
What do I want my rate to be in?
Oh, it's right.
What's my rate gonna be in? Atoms per second.
Yeah.
Huh, well I got the per second part, so what do I have to do now?
Find the atoms.
Find the atoms. Okay, how many atoms is 5.2 micrograms of iodine?
A lot.
Probably.
I got 2.39 times 10.
Something like more than there are people on the planet. So, yeah.
By a lot.
By a lot.
Yeah, by a lot.
People on the planet times a million. Billion?
More, I think. What, there's 7 billion people?
So we have 5.2 micrograms, and we have, let's see, in 1 gram, there would be 10 to the 6th micrograms, because that's what a microgram is.
It's 10 billion.
So I got rid of that. And there's 131 grams in 1 mole. So I got rid of that. And in 1 mole, there's Avogadro's number of atoms. Oh, look at there, another unit conversion problem. Have you noticed how we're doing a lot of dimensional analysis and ratios?
Yeah.
Because chemistry is mostly dimensional analysis and ratios. Really is. You just gotta figure out what you're doing, you know? All right, so we got a number here.
2.39 times 10 to the 16th. A lot.
Did you guys get that?
No, I
You did not get that? Okay. I'll wait to see where we got. What'd you get?
Oh,
What'd you get? You got that?
Yes.
Did you get that?
Pretty sure everything's in.
Okay, cool. Okay. Cool, I've got atoms, I've got per second. Can we find a rate?
Yeah.
I can.
We divide.
So, rate equals Kn. Ka, right? First order rate equals Ka. I'm gonna go ahead and use N because I'm doing a number of molecules here, but it could be Ka. I'll go ahead and make it Ka because that's what we've been saying. Okay, so let's see. I know K. I know A.
1.46 times 10 to the 10th.
Yep. So 10 billion.
Okay, so atoms per second is the SI unit for rate, and it's called a becquerel. So an atom per second in radiation terminology is 1 becquerel, which nobody's ever going to spell out. It's just a BQ. That's BQ. Okay, 1 becquerel. You'll notice the number is insanely large, always. I mean, this is only 5.2 micrograms. This is less iodine-131 than the weight of like an inch of your hair, 1 strand of your hair. I mean, that's how little we're talking about here. So huge numbers of atoms here. So the becquerel suffers from a lot of what a lot of SI units do, and that it's inconvenient. So we put a metric prefix, since people are trying to get away from the Curies, Marie and Pierre, wanted to have a more reasonable sized unit, and it's still used a lot. It's called the Curie, which happens to be 3.7 times 10 to the 10th becquerels. So
It's inconvenient too.
That's horrible.
Why is it-
So what is this in Curies?
Or 1.9?
How much radiation do they get in Curies?
Like 0.4-ish.
.4?
Give or take, yeah.
What does it say? 3.7 times 10 to the what?
10. You can see why people prefer Curies, right? Because it's like a much easier number to deal with. The SI people who insist on always using everything in strictly SI units, we could put a metric prefix in front of this to make the unit not stupid. What could we do? What metric prefix could we put on the becquerels here to make it work?
14.6 mega? Mega's 10, right?
Mega?
That's 10. Is that
That'd be 10 to the 6th. We still end up with like 10,000-ish.
Giga?
How about giga?
Yeah.
Yeah. And so what you're starting to see in the literature, because everybody knows this is stupid, you're starting to see stuff like 14.6 gigabecquerels. So you're starting to see that. I prefer Curies because they're bigger. Okay. But that's what you would do with any unit, right? If that was like meters, you would say, oh, well, let's do 14.6 gigameters. You wouldn't say 1.46 times 10 to the 10th meter or something like. Okay. See how it works?
Yeah.
Okay. Cool. Now I'm gonna remind you of this over and over again, but here we go. I'm just gonna give you my latest thing. Probably do this once a week for the rest of the semester. Following what I am doing on the board and doing it yourself are 2 completely different skills. You can come in and say, I completely follow what you're doing on the board, but when I try to do it myself, I can't do it. The reason why is because it's 2 different skills. Please try to take advantage of the fact that I'm writing it up here and then giving you some time to try to figure out how to do it yourself. Because that's the skill you have to learn. The skill of following what I'm doing is awesome for me because I go, hey, you understood. But you don't until you can do it yourself without me walking you through it. Okay? So remember that. Try to do that. Take advantage of it. All right. Cool. So that's kinetics. Now we're going to take these kinetics and we're going to do something with them. And what we're going to do with them is we're going to look at those kinetics when we had the arrows going both ways, like we had right here. Let's go right here.
Oh, equilibrium.
So that one right there, for example, the forward and backward rate are the same. And so if you were to take a look at a graph of this, you would say, hey, here's my BR2. And here's my BR minus. And that point where they cross, where the rates are the same, is that rate we're talking about right here, where they end up being the same. The example I like to use is an aquarium. So you got an aquarium, you got two aquariums. And you've got, one of them's filled with water and the other one's empty. And so I get two students to come up here and I say, okay, you get the bucket, you get a cup. So I got a bucket, I got a cup. And I say, here's what we're gonna do. You're gonna stick it in like this, and you're gonna take the water and you're gonna put it in the other side. So the first time they do that, the person with the cup doesn't have anything to put in there, and so I guess they pour air in there. You know, the other person puts a cup of water in. A bucket of water. Next time, the cup person, wow, almost filled the cup. Put in some, there it goes, bucket comes over like this. Pretty soon, that cup person is going to be putting a full cup in every single try. But as the bucket person comes down, the water level in the aquarium is going to go down, and you're going to start getting less and less water in the bucket. At some point, the water level is going to be such that the amount of water I can put in the bucket is exactly a cup. And then I've got a cup going in, I got a cup going out, and I don't care how long you do it, the water levels are not going to change. That point where that happens is called equilibrium. Now there are two kinds of equilibrium and one kind of equilibrium. One that'll fake you out, nothing it's equal. The first kind of equilibrium is what's called static equilibrium. Static equilibrium is like those rocks that are sitting on the pinnacles in Utah. You know, they're just hanging there. Or if you've watched a Roadrunner commercial, those ones, or Roadrunner cartoon, those rocks that are sitting there on top of those spires. That's a static equilibrium. It's just hanging there. It's not moving. It's staying. There it is. Okay? That's pretty rare in chemistry. The other kind of equilibrium, the one that we're going to be dealing with, is what's called dynamic equilibrium. And that's the one like I was talking about with the aquariums. There's a constant back and forth between the water, but the levels of water are not changing. In a dynamic equilibrium, there's a constant back and forth. You can actually prove it pretty easily, probably not with this reaction, but if you took some BR2, if you did this reaction and you said, okay, I'm gonna take out a little bit of the BR2 and I'm gonna replace it with radioactive BR2. It's already at equilibrium. The levels are never gonna change, but what you'll see is the radiation will move over to the other side until I got equal amounts of radiation on both sides, even though the levels never change, which shows that it's dynamic. There's a constant back and forth. It's just the rate forward and the rate back are equal to one another. Okay. There is a third kind of semi-equal, I guess, I don't think it really is equilibrium. Maybe it is. And that's called the steady state. And a lot of your biology majors or biochemistry majors, so this is huge for you. So in dynamic equilibrium, this is the direction we're going. But there's another way to keep the levels the same. And if we continue with our water analogy, imagine that you're sitting in the bathtub and you open the drain, but turn the water on. If the water inflow coming from the faucet and the drain are draining at the same rate, you will never see a change in the bathtub level, because the coming in rate and the going out rate are exactly the same. And that's called steady state. And most of your enzymatic pathways are steady state, because you've got something coming into that pathway, you got something coming out of that pathway, and so you have a constant level of stuff here in the middle. Which is why screwing up one of those pathways causes such problems. Because now imagine that you don't let the drain, you close the drain. Now what's going to happen? Your bathtub's going to overflow. Because I still got it coming in, but now I can't get out. So for example, you see in a can of diet soda, it says, warning, phenylketonuria, don't drink this stuff, right? You've all seen that warning label on your diet soda. Why? Because they have a defect in their phenylalanine to tyrosine pathway.
Sure.
And so when phenylalanine comes in, it cannot, it's stuck, the drain doesn't work. And so bam, phenolphthalein builds up. You get too much phenolphthalein building up, it starts interfering with nerve function, and you end up having serious mental issues. So that's steady state. Okay, most of what we're going to talk about here is dynamic equilibrium. So let's talk about equilibrium. So if you have equilibrium, and let's just say that these are all in solution. Then equilibrium, which goes by a capital K. Yes, we've horribly overused K. As a matter of fact, the rest of the semester is all equilibrium. Okay? There's like 4 or 5 chapters in your textbook that are equilibrium. But it's like, here's equilibrium. Here's equilibrium for acids. Here's equilibrium for salts. Here's equilibrium for blah, blah. Here's equilibrium for this and that and the other and whatever. What I want you to remember is the stuff we're talking about when we start talking about the basics of equilibrium, when I start applying it to a new system, it doesn't change anything. It's still the exact same equilibrium. It's all exactly the same. All the rules we're learning right now are going to apply no matter what the system is. Okay. So equilibrium is products over reactants raised to the power of the coefficient ignoring liquids and solids.
Very.
Ah, does that sound familiar?
Just a little bit.
What is that?
It's Q.
Q. Q was the equilibrium constant at non-equilibrium conditions. Now, why did we use Q instead of K for electrochemistry? What does it mean when you're at equilibrium?
K means constant.
It means the forward and backward rates are the same,
That means
right?
your voltage is like 0?
My voltage is a 0. The reaction's done. If I'm in equilibrium, the reaction's done. So I never care about K when I'm doing electrochemistry, because that's saying I got nothing. You know, I guess if that's exciting to you, then you can calculate it, but nobody does, because dead batteries are not interesting unless you're a recycler. Okay, so in this case, we would do it just like we did before, right? It would be C to the C power, D to the D power, over A to the A power, and B to the B power, right? Just like we did with Q. So it's exactly the same as Q. Now, let's take a look at that for a second. So this is what K is. What if I'm not at equilibrium, i.e. we're at Q? What if Q is bigger than K? So K is where the reaction's done. We got the right number of reactants and products. They're all done, it's all awesome, and it's gonna stay there forever. But Q is bigger than K. So pull out some algebra and tell me what that means. What do I have too much of? I have too much product, right? You see that? Because numerator is too big, right? So, which way does the reaction have to go? It's gotta go backwards. Because my numerator's gotta get smaller, my denominator's gotta get bigger. I gotta get K. K's where I'm trying to get to. So if Q is bigger than K, then I know the reaction is gonna go backwards. So what would tell me the reaction still has some more to go? If Q is less than K, right? In that case, I don't have enough products, so I need to form more. Right? Think about those concentration cells. Do you remember how we always had to have the smaller number on top? Because we needed it to be negative? Because we need the reaction to still want to go to products. That's why we always put the smaller number on top. Because the reaction wants to go to equilibrium, and that's to take it towards product. Okay. So that's equilibrium. What we just described about how if you've got too much product, you now have a higher rate, right? Because rate equals Ka. So if I increase A, I got too much rate. So if I've got my product's rate is higher than my reactant's rate, right? Because I've got too much product over here, I got too much rate. So it's gonna shift that way because this one is bigger than this one, right? I mean, that's how it works. That was first figured out by a guy named Le Chatelier. And it's called Le Chatelier's principle. Probably should be make it possessive. Okay, Le Chatelier's principle. It's also called, depending on where you go look, because you guys don't trust me and want to go out to a Khan Academy or something, sometimes it's called the law of mass action. Same thing. Okay, so Le Chatelier's principle. To put it in words, Le Chatelier's principle says, if you stress a reaction, the reaction will move to get rid of the stress. Okay, that's what it says. So if you put stress on a reaction, i.e. you got too much of something, it's gonna move in such a way to relieve that stress and get back to equilibrium. Here's something that may help. Remember a couple of years ago when everybody was wearing those yellow plastic rubber bracelets, the WWJD bracelets? That was like a big deal 4 or 5 years ago. And there was also the bicyclist guy who was raising money for something. So anyway, you got these bracelets, but we're gonna have a different bracelet. Our bracelet is gonna be a WWWD. Okay? What would water do? Okay? Ask yourself, what would water do? So here we go. I'm in equilibrium. What would water do? Nothing. It's a lake. Oh, hold it. Let me add some reactants. What would water do?
React.
Move to products. I add some products. What would water do?
Move to react.
Move to reactants. I remove equal amounts of reactants and products.
Nothing.
Still doesn't do anything. I remove reactants.
Move.
What would water do?
Move to reactants.
You always get the right answer. What would water do? Just ask yourself what would happen, treat that. Now, here's another thing. What about heat? So let's say this is an exothermic reaction. If it's an exothermic reaction, where would I put heat in this equation? Is it a reactant or a product? It's a product, right? Because you get hot because the chemicals lost heat. That's why you get hot.
Yeah.
So if we have an exothermic reaction, the heat's over here. I add heat. What would water do?
Move to reactants.
That's why you have a 600-pound engine block in your car. It's not because you need a 600-pound engine block. It's because when you're trying to burn gasoline, which is exothermic, you don't want that heat building up in the engine because it's going to shift the reaction back towards gasoline and away from products. You will get a less efficient burn. What if it was an endothermic reaction? What would it do? It would shift to products, right? Because now heat's a reactant. It's going to shift that way,
Sure.
right? So, for the purposes of Le Chatelier's principle, heat is like another chemical. Where's the heat? Which side is the heat on? If it's on the reactant side, it's going to shift it to products. If it's on product side, it's going to shift it to reactants. Right?
Yeah.
Okay. Cool. So that's Le Chatelier's principle. So, oh, let's see. What are we going to do? Let's do. Oh, let me do you one more thing. First off, everything's going to be K, but we're going to have like a million different subscripts. We're going to have a KA, KB, KC, KD, no, KF, KH,
Why not E?
KL, KM. Yeah, biochemist, you're really going to get KM a lot. That's Michaela Smith and constant. KNO, PKP, KEQ, KSP. There's like a million of them. Okay? They're all equilibriums. Okay? They're all equilibriums. Just remember that. And we're out of time. So I guess I'll see you on Wednesday. We'll keep going.
It's just like I wonder.